All right, today we're going to peel back the layers of reality and take a look at the fundamental rules that, well, govern everything. We're going to start with the tiniest building blocks you can imagine and work our way all the way up to the master blueprint that organizes them. Yep, this is chemistry, deconstructed.
I mean, it's a question that people have been asking for, well, forever. And the answer isn't just, stuff. It's actually a hidden universe of these unbelievably tiny particles, all locked in this constant energetic dance that creates the very world we see around us.
Think about it. Everything you can touch, see, or feel, the solid ground, the water in your glass, even the air you're breathing right now, it's all made of the same basic particles. The only real difference between a solid, a liquid, and a gas is just how tightly packed those particles are and how fast they're zipping around. It's like this invisible ballet happening constantly all around you.
Okay, so to make sense of all this, here's our game plan. First, we're going to meet the particles themselves. Then we'll see how chemists actually sort them out. After that, we'll get into how they stick together, what happens when those connections change, and finally, we are going to crack the code of the periodic table. All right, first up, let's get properly introduced to the main characters in our story. I mean, who are these particles that make up, well, everything? So you've really got three key players to keep in mind. First is the atom. Think of it as the smallest, most basic unit of an element, like a single Lego brick. Then you have the molecule, which is just what happens when you snap two or more of those atoms together. And finally, there's the ion. That's just an atom that's either gained or lost an electron, which gives it an electrical charge. Seriously, if you get these three, you've got the foundation for everything else. Okay, but in the real world, these particles are almost never just floating around by themselves, right? They're all mixed together. So how on earth do scientists separate them out to actually study them? Well, let's take a look inside the chemist's toolkit.
Okay, two classic techniques you'll see are filtration and crystallization. Filtration is pretty much what it sounds like. It's like a microscopic pasta strainer. It's perfect for catching something that won't dissolve, like if you had sand mixed in water. Crystallization, though, is for the stuff that does dissolve. You just let the liquid evaporate away, and what's left behind is the solid, forming these really pure crystals.
And then you've got distillation, which is a really powerful method. Let's say you have salty water. You boil it, right? The water turns into steam, but the salt gets left behind. Then you just capture that steam, cool it down, and boom, it turns back into pure, totally drinkable water. It's an absolutely brilliant way to separate liquids that have different boiling points.
Okay, so we know what these particles are, and we know how to separate them. But how do they actually stick together to form, everything? From a drop of water to a diamond? Well, it all comes down to the rules of attraction, or as chemists call it, bonding.
Now, there are two main types of this, let's call it atomic glue, and it's all about the electrons. In what's called ionic bonding, one atom literally gives an electron to another one. This creates these charged particles, ions, that then stick together like tiny magnets. But in covalent bonding, the atoms share electrons instead. The whole reason they do this, either way, is to become more stable. And that choice, to transfer or to share, is what gives our world its absolutely incredible diversity. Let's actually see this in action. Here on the left, you see a sodium atom giving an electron over to a chlorine atom. Bam! That's how you get table salt. A classic transfer, a perfect ionic bond. And on the right, you've got two chlorine atoms. And to be stable, they each share electrons with each other. That's a textbook covalent bond, forming chlorine gas. And get this, the way the atoms are bonded can change absolutely everything. Take a look at diamond and graphite. They are both made of nothing but pure carbon atoms. That's it. But in a diamond, the atoms are locked into this super strong, rigid 3D structure, which is what makes it the hardest natural thing we know of. In graphite, though, they form these weak layers that can just slide right past each other, which is why it's soft enough to be in your pencil. I mean, same atoms, totally different bonds, and you get completely different materials. It's amazing. So, atoms stick together. We've got that down. But what happens when we break those bonds and form new ones? Well, that, my friends, is the very essence of a chemical reaction.
You see, every single chemical reaction involves a change in energy. It either releases it or absorbs it. Exothermic reactions, things like a fire, they release energy. That's why they feel hot. Pretty simple. Endothermic reactions do the exact opposite. They absorb energy, which makes their surroundings feel cold.
A perfect example is photosynthesis, where a plant is literally pulling in energy from the sun to make its food.
Another huge part of a substance's chemical personality is its pH. You've probably heard of the pH scale. It's basically a way to measure how acidic or alkaline something is. The scale runs from 0, which is super acidic, all the way up to 14, which is super alkaline.
And smack dab in the middle of that scale, the number 7. That is the pH of pure water. It's the perfect balancing point of the chemical world. Not acidic, not alkaline, just perfectly neutral.
Okay, let's do a quick recap. We've met the particles, we've sorted them, we've seen how they bond and how they react. Now, it's time to meet the master blueprint, the cheat sheet that organizes it all, the periodic table.
Now, this thing is so much more than just a chart you see in a science classroom. It's a predictive map of every element in the universe. It organizes them by their atomic structure. And here's the magic part. Elements in the same column, what we call a group, all share similar chemical properties. It is an unbelievably elegant way to make sense of all matter.
The table's real power, though, is how it reveals patterns and trends. Just look at group 7 here, the halogens. As you move down the column from fluorine to iodine, you can see this beautiful, clear pattern. They go from being a gas to a liquid to a solid. And look at their boiling points. They just steadily climb. The table lets us predict this stuff without ever having to step foot in a lab. It's incredible.
And this knowledge isn't just for textbooks. It has huge real-world power. By mixing different elements from the table, we can create things called alloys, which have way better properties. For example, you mix a tiny bit of carbon with iron, and you get steel, which is massively stronger than either of them on their own. We literally use the periodic table to engineer the materials that build our entire modern world.
So, there you have it. We've gone from the super simple idea of tiny little particles all the way up to this incredible map that explains exactly how those particles behave and interact with each other. It's really a journey from the invisible world of the atom to the universal laws that govern, well, everything. Because at the end of the day, understanding chemistry isn't just about memorizing facts and figures. It's about understanding the fundamental rules of reality itself. It's like being given the ultimate toolkit for creation and innovation. So really, the only question left is, what are you going to do with it?